We'll do a couple of examples using things from previous videos before we get into the next subject, which is going to be power spectral density. I'll leave that for another video. So let's do a couple of examples. Consider a wide-sense stationary Gaussian process, we're told that, and it has this autocorrelation function. What's the probability that the absolute value of any x is greater than 4? It'll work for any t because it's stationary. It's Gaussian, so all we need to know is its mean and variance. And since the limit of this as tau goes to infinity is 0, then the mean is 0. That means the variance is just the mean square value, and that's just the autocorrelation function evaluated at tau equals 0. Which is going to be 4. That's the variance. So the standard deviation is the square root of that, or 2. This 4 is how many standard deviations? 2 standard deviations. So we're just looking for what's the probability that we'll go outside of plus or minus 2 standard deviations. That's about 5%. If you want a precise answer, you got to use a table or a computer. It's 4.55%. That was a pretty easy example. Let's see this. Another wide-sense stationary process with a given autocorrelation function. And again, we know the mean is 0 because this limit goes to 0. Why is this linear function of another random variable x? Well, we're given the autocorrelation function of x. Find the autocorrelation function of y given it has this relationship. So this is what we're looking for. And remember, it's a linear combination of x, and x is wide-sense stationary. So that means from one of our properties, that means y is wide-sense stationary. So that's how we know right here the autocorrelation function is just a function of tau, not 2 times, not 2 absolute times. It's y is wide-sense stationary. And what does that mean? By definition, it means this: y at t and then y at t plus tau. Then something we're going to do a lot, where this random process is a function of another random process or a random variable. You just substitute in. So where we have y of t, we put in this, and y of t plus tau, you put in a t plus tau there. So we find that expectation. We'll multiply out these terms. When you do, you have this. First term is this, x of t and x of t plus tau times this a times a, or a squared. Well, this expectation is just the autocorrelation function of x. These two, well, what do we have here? A times b times x. But this expected value, because the mean of x is 0, this is 0. And that third one is b times a times x of t plus tau. Again, that expectation, that's a mean of 0. Then the last term is b squared. It all reduces to this. And we know what r of x is. Found the autocorrelation. Two fairly easy examples. Anyway, the next subject for random processes, we're going to get into spectral analysis. Oops, power spectral density. We'll save that for many other